In this section, we're going to be talking about how the awareness that we've developed throughout algebra, really understanding what it means to do division, what it means to do multiplication, why factoring is in any ways beneficial to us, how having some awareness and having a comfort with this idea of play can make very difficult problems into very simple problems. So, for example, let me give you a couple of real-world contexts, and we'll circle back to them afterwards. So here's the first question. Let's imagine that we're working to design equipment for a hospital. Perhaps we're trying to monitor somebody's blood pressure. Now, the question is, what would be the best way to indicate to somebody if someone's blood pressure was off? We could, on one hand, always have a constant reading of someone's blood pressure. If that's the case, then we would have a display, we'd have a monitor, we'd have a constant flow of information, and somebody who would be responsible for watching that all the time. That does work. But maybe a more efficient method would be we just set some kind of cutoff point for when someone's blood pressure reaches a peak that we should pay attention to. Then an alarm could sound and somebody could move into the vicinity to take a look at what had caused the change or what had put somebody into a risky situation. Similarly, let me ask you, what about in the stock market? Let's imagine that I wanted to purchase some stocks, but maybe right now the price of the stock is too high. I want to wait for it to go lower, get a better deal. Or maybe I want to wait for to purchase something at the store, but right now the price is too expensive. I want to set a little monitor over there and I want to watch it when it dips. What would be an indicator for when I should be making these purchases? Again, we can set up some kind of alarm that just simply says when the price drops below, I don't know, maybe $3 a share, or when the price for the shirt that I'm looking at comes below $15, that's when I should start paying attention to the thing that I want to go and purchase. And similarly, let's talk about how we might monitor populations of people. So let's now talk about, is it if we know that there are people who are moving from Illinois up into Wisconsin or Wisconsin down into Illinois, is it best to know that movement of people by going and counting all of the people in Illinois and all the people in Wisconsin and then doing a difference comparison? Or could we just simply set up somebody at the border to click on a little monitor every time somebody steps over? Now, this idea is a powerful one, and it's what we're going to talk about today in math, because we're going to be dealing with inequalities, something that oftentimes we use to say statements like greater than $3 or positive or something that is anything but positive, in other words, zero or negative. And so we're going to be talking about how we can use models like this, use inequalities to capture models like this, and how instead of trying to look at individual points, we can use some logic to allow us to extrapolate to big conclusions from just a few little data points. So let me show you a little bit of what I'm talking about. There's only two problems that I want to show you in today's lecture, but I'm going to kind of walk through them in such a way that hopefully we'll be able to take the ideas and apply them to anything, even if they're not exactly what we're working with today. So here's the question I want to start with. Let's imagine I have this polynomial inequality, this x cubed minus 3x squared plus 2x is greater than or equal to 0. I want to know when it is greater than or equal to 0. In other words, I want to know when it is anything except for negative. Okay, we call those non-negatives. I'm trying to figure out when is the value, whatever answers pop out of this thing, non-negative. Okay, well, let's maybe start off with how I could graph some of this in. So I could always, of course, if I'm confused, fall back to a table of values. Let's do a table of values. That'd be, I'll put in some x values. I will get out some f of x values. And I'll call f of x everything on the left-hand side. We'll label this as all f of x values, and I'll try to look for values that are positive. So we could do some easy ones. Let's maybe start a little bit to the negative. Let's do -2. We'll plug that in. That'll be -2 in parentheses cubed, because I want to make sure I'm repeatedly multiplying the -2 here. And then we'll do -3 times -2 squared plus 2 times -2. And if you multiply all this out, this would get us -8. Let's see, -12 would be -20, -4 would be -24. All right, so that would be -24. We could then do -1. Similarly, we're going to get, let's see, -1 cubed minus 3 times -1 squared plus 2 times -1. And so again, what's it going to get us? It's going to get us -1 minus 3 would get us -4. Minus 2 more gets us -6. And then we go over here to 0. We could plug this in. This would be 0 cubed minus 3 times 0 squared plus 2 times 0 gets us 0 all across the board. And maybe we'll do 2 more. We'll do 1 and 2. 1 would get us 1 cubed minus 3 times 1 squared plus 2 times 1. And so I think that's going to get us 1 minus 3 gets us negative 2 plus 2 gets us 0. And 2 would be the last one maybe we're going to use before we kind of abandon this strategy. So we'll say 2 cubed minus 3 times 2 squared plus 2 times 2. And that should get us 8 minus 12 would be negative 4, plus 4 would get us, we get another 0. Interesting. Let's kind of plot all these out. So I'm going to go ahead and sketch this into my graph. We'll draw a coordinate plane and all this. So we'll set this as being my y-axis. This will be my x-axis, and I can go 1, 2, and 3. And if I go back 2, I would go down 24. That's going to be really far down here. If I go back 1, that's going to be at negative 6. So that'd be 1, 2, 3, 4, 5, and 6 would go right here. And then the next one would be 0 and 0. After that, we would have 1 and 0. After that, we would have 2 and 0. Okay, so not a lot to be able to sketch out our curve. Let's see if we can fill this in. We'll jump over to a computer graphing software called Geogebra, and we'll get an idea of what this looks like to kind of confirm what we're playing with. Okay, and sure enough, it looks like this is exactly what we're playing with. It's going to go steeply down, it's going to cross through the origin, it's going to come down below the 1, and then go back up for the 2. So let's go ahead and sketch that in. So we've got our curve. Our curve is going to be something like here, where it comes up, goes down, and goes up again. Okay. But suppose that we didn't have this curve. Imagine that we didn't have the ability to graph it. Is there a way that we could get a good idea of what's going on here? Well, here's the idea that I have. In between all of the times where it is a 0, right? So like, for example, when I'll put my x values down here, my f of x values up here. So this will be when my x value is a 0 on the number line, that's going to get me an f of x value that is also a 0. This is my point 0, comma 0. New way of modeling it. Negative 1 got us negative 6. Negative 2 got us negative 24. And then it kind of, we can assume that it stayed negative over there. So actually, if it only comes up to hit that 0, that means everything over here is negative. So I can put maybe like a little negative symbol in here. Then 0, it goes up to 1. That was when it dipped back down. So inside of here, it would have needed to be all one thing or the other. As it turns out from the picture, it was all positive. And then it hit a 0 point again. And then we got to 2, and it was a 0 point again. And between that, it was all negative. And then after that point, it became all positive again. So this gives me an idea. What if, just like our examples, we kind of look for these borderline, these boundary indicators, right? These monitors, if you will, of if I know there are certain times I'm going to cross the 0, then between all of my zeros, I must be either positive or entirely negative. How could we do that from our solution? Okay, so we played enough. Let's see how I would maybe tackle this problem if I was going to try to determine a strategy from scratch. I think I would start off with saying if I had this x cubed minus 3x squared plus 2x, I would first want to understand when it is equal to 0. Because if I can find out when it's equal to 0, then between all of those zeros, I must be either positive or negative. So let's do a little bit of analysis. When would this whole thing be 0? Well, right now I have things that are being added and subtracted from each other. It's a little bit difficult to figure out when this is all going to play out nicely, like when we tried to work it up here. But I do know that if I had this all as multiplication, that it'd be very easy to find out when it's 0. Because if it's all multiplication, that means that one of the things being multiplied would have to be 0. That's the 0 product property. So I could write this entire thing in a factored form. X squared minus 3x plus 2 equals 0. And then I could do my AC method. My AC method says I'm looking for things that multiply to a times c, which is 2, and add to negative 3. So that would be negative 2 and negative 1. So I could rewrite the entire inside here as being x squared minus 2x minus x plus 2 equals 0. Perform my factor by grouping, which means I'm going to pull an x out of the first two things in the parenthesis. That would give me an x minus 2 left over. And then I would pull out, let's see, a negative 1 to try to match up with the x minus 2 I had before. Still equals 0. And I think after that point, I should be able to be all done with my factor by grouping. I have x and a -1 group of x minus 2. Now that's really useful because, again, if I wanted to find out when all of these are equal to 0, that's just as simple as saying when does x equal 0, the first thing I'm being multiplied in, x is 0 when x is 0. When does x minus 1 equal 0? And that happens when x is equal to positive 1. And I could say, when does x minus 2 equal 0? And that happens when x is equal to positive 2. So after I find all of these kind of boundary points, then I can go on to my number line, and I can say those are the only values that I really need to put down here, is when x is either 0, x is 1, or x is 2. Now those are the times where I'm going to be equal to 0. Everything between that's going to be positive and negative. It has to all be positive and negative. So I can pick any point in between these values as a test value to be able to see what is happening in that entire region. So let's first start with everything that's happening before 0. Let's choose a number. Let's make it easy for ourselves. Let's do maybe -1. So we'll plug that in. We'll say into our original f of x, we'll write this as f of -1. f of -1 is going to be -1 cubed plus, or minus 3 times -1 squared. Which would be plus 2 times -1. And all in all, that's going to get us, what? I think we did it all the way up here, right? That gets us -6. Now, the important thing about this is not the -6. It wasn't even the -1. It's the story for why I did all this. I chose a point before I had reached 0 as a representative of the sign for everything over there. In other words, by choosing something before 0 and combining it with my logic of saying I hadn't yet hit my 0 mark, I hadn't yet hit my f of x equals 0 mark, that means if one of the values over here was negative, the whole value was negative. And if we need to, let's go back up here to our picture to see why that is. If this is where our 0 mark is right here, and right here, then I'm just choosing any representative like my -1, and I'm saying, look, over here, it was a negative height. That means that everything else was a negative height. Otherwise, somewhere over here, I would have hit my x-axis again. I would have had f of x equals 0. So we're choosing a representative. We're saying it's negative at one of the values, therefore it must be negative at all of the values before 0. Okay, good. Let's keep going with that one. What about f of, it looks like the next gap would be between 0 and 1. So maybe I'll choose, I don't know, 1/2. 1/2 seems like a pretty reasonable choice. So let's do 1/2. That would be 1/2 cubed. Notice the parentheses are going to be very important here. Minus 3 times 1/2 squared. Plus 2 times 1/2. Oh, running out of room here. And we would say that is equal to 1/2 cubed would be 1/2 times 1/2 times 1/2 would be 1/8. -3 times 1/2 squared would be -3 times 1/2 times 1/2. That would give me -3/4. And then 2 times 1/2 would get me just 1. I can make these all into common denominators and say this would be 1/8 minus 6/8 plus 8/8. And I think that's going to get us a total of 3/8. So because 3/8 is greater than 0, that must mean that everything in between 0 and 1 is greater than 0. In other words, everything in here is positive. And you could repeat this again and again. Let's choose a number between 1 and 2. We could do 1/2 or 3/2. So let's do that. f of 3/2 would get us 3/2 squared. Or sorry, excuse me, 3/2 cubed minus 3 times 3/2 squared plus 2 times 3/2. And if you do all of this in between here, you're going to see that it actually comes out to be a negative value. So that would allow us to say something like f of 3/2 is a negative value. It's less than 0, and that could be our conclusion. So we'll come up here and we'll put in a little negative symbol. And then again, you could do this again for the 2. And as we've kind of seen above, it's going to become positive. Choose any value. You want to do 3, do f of 3. You want to do f of 500, do f of 500. Either one of these, you're going to be able to plug it in the same way we just did, and you're going to see that that 500 gives me a answer that's positive, so everything after 2 must be positive. So this is a nice way of kind of doing things without having the ability to graph stuff. If we have the ability to graph stuff, it definitely makes it quicker. If it doesn't, then this becomes our strategy. We'll abstract this out to a couple of different steps. So step one, what was it that we did? Step one was we looked for all of the boundary points. Okay, so that was something we did through factoring. So boundary points, we can write down here, what is a boundary point? It is an x value that makes f of x, whatever we want to call f of x, equal to 0. So it makes f of x equal to 0, and it's used for inequalities like f of x equals, or f of x is greater than 0, f of x is less than 0, or we could have also done it for f of x is greater than or equal to 0, and f of x is less than or equal to 0. Because originally, let's remember our question. Let's also make sure we don't lose track of that one. Solve the inequality for when this whole thing happens. This whole thing happens, it's greater than 0 between, it looks like 0 and 1, and then after 2. So through all of this work, we could say that our final answer is that between 0 and 1, and after 2 are the x values that give me something that is greater than 0. So that would be our final solution. Good. What is a test value? A test value is the function or let's write this differently. Let's say it's an x value used to represent the sign of a function between boundary points. Okay, excellent. We've got our strategy now. Now, as it turns out, this strategy is so robust that you can use it with polynomials. You can use it even when you have rational expressions. But for rational expressions, we have one extra little detail. So let's take a look at this one down here. So solve the rational inequality. This time we're going to try to use our strategy to get us our picture, or at least an estimate for our picture, and we'll use the GeoGebra on the back end to see if we've been able to capture everything that the computer did just in an idea format. Okay, so solve the rational inequality. When does all of this stuff become greater than or equal to 0? Okay, this one requires a little bit of thought again. We definitely want to find the times that the function, this thing over here, which we could call f of x, we could say, when does this whole function here equal 0? Because if that thing becomes 0, then that's a boundary point. We can put it on our number line and we can consider things on either side. Okay, so let's play around with that one first. So we'll say for our boundary point, we're going to do when does x minus 4 over x plus 1 times x minus 8 equal 0. Now, if I think about it, fractions can only equal 0 whenever the numerator is 0. The denominator can't be 0. You can't divide by something that gets you to 0. But you can always have a 0 on the top of the numerator, or top of the fraction that gets me a 0. So if the 0 is numerator, that's the only, if the numerator is 0, that's the only thing we need to be able to say this entire thing is 0. Another way of thinking about that is that you could try to multiply the denominator away and you'll get to the exact same thing I'm about to write. X4 equaling 0 is the only thing that's going to make this entire thing 0. And that happens when x is equal to 4. Okay, so we've got our boundary point. Now the other interesting thing though is this is when I was equal to 0. But if I look back at my original problem, there's also the possibility of me being negative or positive depending on the denominator. That feels a little bit weird. Let's come back to that one in a moment. So we're going to come over here to our number line. We're going to sketch down what we figured out already. X equals 4. So I could then say, okay, let's pick something to the left of 4 as a test point, and let's pick something to the right of 4 as a test point. And that would tell us whether the numerator had originally been positive or had originally been negative, and did it switch and become positive, or did it stay as negative? What happened after that boundary point? But this only asks about what happened at the boundary point. I'm also noticing here that if the denominator ever switches from positive to negative, then that's going to be a change from me saying I'm dividing by a positive number to I'm dividing by a negative number. And that has the possibility to switch the entire structure, the entire negative positive result of this fraction. So perhaps let's just take a look, just to be cautious. Let's consider, when does the denominator also switch from being positive to negative? So we're going to find out, when does this thing become 0? That would be when x plus 1 equals 0, or when x minus 8 equals 0, which would be x equals negative 1 and x equals positive 8. And so let's just put that down on our number line just to play. We'll put negative 1 and we'll put positive 8. And let's just see if those values were in fact important. There's nothing wrong with us putting too much down here. Okay, so we've got the boundary points. Those were x equals negative 1, x equals 8, and x equals 4. Let's now try our test values, right? So for our test values, let's organize it nicely so that anybody can follow our work. We've got our boundary points, we've got our test values. Okay, let me make sure I'm calling it right. Yep, test values, good. Let's choose some test values that are between here. So before negative 1 would be a nice place to start. Let's choose a number smaller than negative 1. That would be, negative 2. So let's try and find out what happens at negative 2 as a representative for everything that happens before negative 1. So let's plug that in. That'd be negative 2 minus 4 divided by negative 2 plus 1 times negative 2 minus 8. Okay, solving this out, this gets us negative 6 divided by negative 1 times negative 10, which gets us negative 6 divided by 10. Okay. I could write that more simply by saying it's negative 3/5. But the important thing is that this is less than 0. Okay, so we're going to put that in over here. This is where I am negative. Here was where I was 0. Okay, good. Let's do a test point between negative 1 and 4. Let's maybe choose 0. That seems pretty easy. So let's do f of 0 as our representative between negative 1 and 4. F of 0 is going to get us 0 minus 4 divided by 0 plus 1 times 0 minus 8. That gets us negative 4 divided by 1 times negative 8 is negative 8, which is just simply 1/2. But the important thing for this is that here, this is greater than 0. So that means everything in here is positive. Interesting. Okay, so I went from negative to positive. And notice, that was one of the points that we were curious if we even wanted to continue or consider, was what happens with the denominator. So it turns out that the denominator switching in the signs was actually quite important for us. So we wanted to include that value as something that may be important for us. And in fact, we can even see that that sign happened. Notice that in the negative 2, when I plugged in my negative 2, that made my denominator a positive 10. But when I plugged in a 0, it made the denominator a negative 8. So sure enough, if the denominator switches from positive to negative, that's an entirely important point to be paying attention to for what the sign is of my answer. All right, let's now do another test value between 4 and 8. Maybe we'll choose 5. Again, you could choose 6, you could choose 7, you could choose decimals, you could choose fractions. I'm just going to choose nice numbers because there's no reason not to. So that'd be 5 minus 4 divided by 5 plus 1, and then 5 minus 8. This should have been, because we chose 4 as a place where my numerator switched signs. Let's see if that comes out to be. 5 minus 4 is a positive 1 divided by 5 plus 1 is 6 times 5 minus 8 is a negative 3 times negative 3. And sure enough, we can see that now my numerator, which used to be negative, it was a negative 6, and then it was a negative 4, is now a positive 1. So sure enough, we wanted to kind of capture where that happened. That's going to happen when we get, 1 over negative 18, which again, the important thing for this is that that's just less than 0. So I can go up here to my picture and say, at 4, I had a 0 again, and then after that, I had a, negative value. Oh, I'm actually looking back on this. I don't think I had a 0 at negative 1. I think I might have written that wrong. That's when my denominator was equal to 0. So I actually had a 1 over 0 that happened at this moment. That's really curious. Let's come back and figure out what's happening with that in the picture, but we'll move on. So again, f of at 8, that was when another place where my denominator was 0. That'd be a 1 over 0 that's occurring there. And I'm curious about a test value that happens after 8. Let's choose maybe 9. So let's do f of 9 equals, and this should be, again, a time when the denominator switched over, because this was a time when I was looking at when the denominator was 0 and maybe switches. So f of 9 would get us, let's see again, 9 minus 4 over 9 plus 1 times 9 minus 8 would get us 5 over 10 times 1 equals 1/2, which is positive. Okay, so again, we switched over to being positive here, and the reason is because, sure enough, we recognized when the denominator switched its sign, so that caused our denominator, see, the numerator was positive 1 before, and now it's a positive 5, but the denominator in the problem before it, or the situation before it, was a negative 18, and now it is a positive 10. Okay, good. So that means it's positive after here. Okay, lots to do there, but we should have found something that instead of finding lots of individual points, we should be able to get something like a behavior. So let's sketch it all in and we'll compare it to our GeoGebra and be done. So let's go ahead and graph in. Maybe I'll choose to put my graph right here. Okay, what are some important points that I did note? I do know that at -1, maybe I'll scale this out a little bit, or yeah, let's scale this out. Let's make this -1. We'll make each of these blocks be a half block this time, just to kind of stretch it out. Is that going to give me enough space? Maybe not. I don't think it's going to give me enough space. Maybe we'll put this right here. That seems better. Okay. So I'll change the color. So this will be, we'll make this -1 right here. That would make over here +1, +2, +3, +4, +5. I needed to get up to 8. It's not going to work. Okay. We'll make each block be 1 unit. 1, 2. I'll label this in to keep us track. 1, 2. So it's -1, +2, 3, 4, 5, 6, 7, 8. Good. It fits what I need. 9, 10, 11, and 12. Okay, 12. And then we'll have it go up here the same way. So it'll be 1 and 2, 3 and 4, 5, 6, 7, 8, and 1 and -2, -3 and -4, -5 and -6. Okay, good. Let's go through and try to sketch this. I'll use a color pink. So things we know. We know that if I plug in a -1, that was a time when my denominator equaled 0. Well, then I shouldn't have an answer that's happening there. I can't divide by 0. So that means, okay, all the way up and down this thing, there is not going to be an answer. I'll put a dotted line as an indicator that I went all the way through here and I couldn't find any single place to put a point. So we'll just put that as an indicator for right now. And in fact, when x was equal to 8, that was another time when my denominator was equal to 0. So that's going to be another place where I can't exactly plot a point, but I'll just do a little dotted line there as a reference. Okay. Let's see what happened at 4. At x equals 4, that was a place when my graph equaled 0, so that does give me a place to plot a point. I can plot a point right there. Before my -1 line, it looks like we were negative, so there was some kind of negativeness happening over here. And then it looks like it switched into the positive realm, so over here it switched into positive realm. And then it looks like it switched into negative realm after 4, so then I went back here in a negative realm. And then after that, it looks like I went back into positive realm. So I should be able to draw something that kind of started in negative values and then went up to positive values, came down to negative values. So here is my guess for capturing everything we have, is that we have something that kind of has negative values and got closer and closer to that dotted line. From over here, we probably had something that did some kind of weird squiggly, has to cross through the point we did recognize, and then again comes close to this dotted line. And then here I started in the positive values again and probably never went negative, so I must have just stayed always above it. Now let's check back to Geogebra and see whether or not I recognized everything correctly according to how the graph was produced. So I've already got it kind of preloaded in. This was our polynomial that we just looked at. Let's turn that one off. Here's everything we have, x minus 4 over x plus 1 times x minus 8. Let's click it in. And sure enough, that's about what we had looking at. So let's reinterpret all of our answers. We had negative values that happened until I had a divide by zero error. And as I had a divide by zero error, that actually is a place, this x equals 1, where I don't actually ever have a value, because you can't divide by zero. It did, however, start to make this very big and very small as I divided by smaller and smaller numbers. Okay, so I had negative values where my heights were all negative until immediately it switched over to being positive heights. And that continued until I hit to the number 4. After the number 4, I switched into negative heights again. And then after that, I went immediately into positive heights after I crossed over the x equals 8 line. So we can see that our process here is a really nice, efficient method of being able to determine when I am negative or positive, negative, positive, when I am having my divide by zero errors, and when I have my positive zero errors. But let's remember what this question was asking. It asked, when is this entire thing greater than or equal to 0? So let's look through this entire thing for where it was greater than or equal to 0 on our number line. It was greater than or equal to 0. Let's see, not... I'll do red to show the times that it's not. It was not, this was negative, so this didn't work. This was a divide by 0, so this definitely didn't work. And then I switched over into positive, we'll use green. Positive happened between the 1 over 0, or between the x equals negative 1 and the x equals 4. Here at the x equals 4, I was 0. That's just fine. I can conclude that one as well. And then I can go all the way until... Oh no, I had negatives there. That wouldn't have worked. So let's take away that because it's asking for when I'm greater than or equal to 0. So then I switched back into a time when I was less than or equal to 0. And then this also is a time when I was not included. We'll do an open circle there. But then after that, I switched back in and continued. So if I wanted to capture all of this using my interval notation, it looks like we picked up negative 1 as a good reference point from our discussion. It goes all the way until 4, but I didn't include negative 1. That was a time when I wasn't positive. I actually had an error. I divided by 0. So we'll use this as a reference with a parenthesis and go all the way until 4, which I include. Then I didn't have anything I included between my 4 and my 8, but then immediately after the 8, I did switch into positive realm again. So I'll say I picked up again at 8, and I went on until infinity. And we'll use parentheses for both of them, because I am not including these kind of reference points. I'm just including things that happened very much near them. So here you have it. These would be the x values that correspond with us being this equation being greater than or equal to 0. When you are right after negative 1, right after this divide by 0 error, and again, it looks like that corresponds very well with our picture. Those are times when I had positive heights. And then I was okay right here as far as saying this was a time when I had a 0 height, which is included in my question. And then we picked up again right after 8. There you have it. Right after 8, right after negative 1, and all the way until 4, which we include. Excellent. So allow yourself the time to play, but make sure that you keep your work very nicely organized for here. You should be identifying where your boundary points are. You should be marking them on a number line. You should be including where these divide by 0 errors are, where these 0 values are between if you have negative and positives, and make sure that you're showing all of your test value work here and very clearly identifying whether or not it is something that is less than 0, like we had here and here, or sometime when it is greater than 0, which we had here and we had here.